So modules 1 and 2 have been all about brushing up on, reviewing, hopefully not seeing for the first time, different concepts from previous math courses. Some of those algebra skills that you're going to need as we move forward into the calculus topics for this course. Module 3, we encounter our very first actual calculus topic, so our first module that should be new material. And what we're talking about in Module 3 is evaluating limits. So before we actually get into talking about what limits are, any formal notation or definitions, we just want to talk about describing the behavior of a function. So given this function below that we'll call f of x, we just want to discuss the behavior of this function, and more specifically, we want to talk about what's happening around these different x values. So I've got that around in quotes because, again, we're not getting into any formal definitions yet, but by around what we mean is what's happening at that point, what's happening as we approach that point. So again, just the behavior of graphs. So first we want to start off by considering what's happening at the point x equals -1. So we can add a little bit of notation here to our graph just to make sure this is straight. So our horizontal axis is always going to be our x-axis. Vertical axis is always our y-axis. So we want to consider, as we head to x equals -1, what is our function doing at that point? So we can trace up until we hit our actual function value. So in this case, the first thing we could start by noticing is that f of -1 is equal to 4. So since we have that filled in circle, that indicates our function is defined there. That point exists on our graph. So that's the simple thing we can talk about, whether or not our function is defined if there's a point. Now what we want to talk about, which is a little bit new, is the idea of what's happening as we approach that value x equals 1 from the left and right-hand side. So as we approach from the right-hand side, we can trace along this graph. So as that x value decreases to -1, what's happening is we're getting closer and closer and closer to that function value of 4. So without, again, any formal notation except for these arrows that we're going to use, what we can say is that as x approaches -1, our function value is approaching 4. So by that arrow, I just mean approaching, getting closer to, again, as we trace along this graph, we're getting closer and closer to that function value. So now we can look at the same thing as we approach from the left. As we approach from the left-hand side, we're still getting closer and closer and closer to that same function value of 4. So in this case, as x approaches -1, our function value is approaching 4. From the left and right-hand sides. So that's what we want to talk about for each of these remaining points. We're going to look at a couple of other examples. We want to talk about what's the function value as we trace along the graph from the right-hand side, as we trace along the graph from the left-hand side, what function values are we approaching? So the next example we want to look at is x equals -4. So when we consider x equals -4, again, we'll move along the x-axis until we get to -4, and then we have the choice. We can either look at heading up until we hit the function or heading down until we hit the function. So in this case, that open circle means the function is not defined there. So in this case, we would actually want to trace up until we hit this filled in circle, which means our function is defined. So when x is -4, our function value is 3. So again, we can start off by saying that f of -4 equals 3. Now we want to take a look at what's happening as we approach x equals -4 from the left and right-hand sides. So now things are going to change a little bit because we have this break in our graph. As we approach x equals -4 from the right-hand side, so again, as we trace down this graph, we see that from the right-hand side, we're approaching a value that's different from the function value itself. In this case, from the right-hand side, even though the function never equals -2, our function value is getting closer and closer and closer to that value of -2. So we could say that as x approaches -4 from the right, our function value is approaching -2. So in this case, notice that's different than the actual function value itself. We're just concerned with what value are we getting closer and closer to as we approach from the right-hand side. In this case, this point where the function is actually undefined. So as we approach from the left, again, we trace along the graph from the left-hand side. In this case, the graph is getting closer and closer and closer to that actual function value of 3. So we could say that as x approaches -4 from the left, our function value is approaching 3. So again, all we're talking about is the behavior of our function. So far we've got a case where the function value and the value that our function is approaching from both directions are exactly the same. In example B here, the function value matches up with one of those values as we approach from one direction, but not from the other. And that has the potential to happen anytime we have holes or breaks in our graph. So let's go on, looking at what's happening around x equals 2. So x equals 2, again, we would trace down to this filled-in point because that's where our function is actually defined. So we can start off by simply noticing that f of 2, in this case, is equal to -1. And then again, we want to consider the behavior as we approach from the right-hand side. In this case, as we trace that graph from the right-hand side, we're approaching, again, even though the function is not defined there, we're getting closer and closer and closer to this value of 5. So as x approaches 2, from the right-hand side, our function value is approaching 5. Then we can look as we approach from the left-hand side. In this case, again, from the left-hand side, we're getting closer and closer to that actual function value. So as x approaches 2 from the left, our function value is approaching -1. So that case was pretty similar to part B. Now let's take a look at what's happening in part D. So in this case, at x equals 4, our function is undefined. Whether we go up or down, there's no point at x equals 4 where we'd actually encounter the function. So we would state that f of 4 is undefined. There is no function value at that point. But then we can consider the behavior of our function as we approach from the right-hand side. So as we approach from the right-hand side, even though we never hit this value itself, we get closer and closer to a function value of 2. So as x approaches 4 from the right, our function value is approaching a value of 2. And we'll see that the same thing happens as we approach from the left. So in this case, as we approach from the left and the right, we're getting closer and closer to the same function value of 2. So as we approach x, as x approaches 4 from the left, our function value is approaching 2. So the function can be approaching the same value from the right and left-hand sides, and the function can be undefined. In the first example, from the left and right-hand sides, the function was approaching the same value, but the function was defined. So we have a few different cases, kind of a variety of things that our graphs can be doing, different behaviors that we can observe and describe, which is what we want to start doing when we talk about limits. So this approach that we were just applying, this is what's called the graphical approach for discussing limits. Or since, again, we haven't really defined what limits are, we're not using any formal notation, it's more the graphical approach for discussing the behavior of the graph. And after we look at some different examples, then we'll start talking about how we formalize this and what limits actually mean. So the graphical approach works really well because you can look at a graph, observe what's happening, but in some cases, this approach can fail. So this graph below is the graph of the function f of x equals x minus 5 over x minus 5 times x minus 12. And again, we want to consider what's happening around the values x equals 5 and x equals 12. So what's hopefully easy to pick up on at this point is that if we plugged in x equals 5 into this function, we would break that function. The function would be undefined because we would get 5 minus 5, which would be 0. The 0 in the denominator means that that function is undefined. So f of 5 equals undefined. And similarly, if we plugged in x equals 12, we would get a 0 in the denominator. So f of 12 is also undefined. Now, hopefully in your previous algebra classes, you've already talked about how to identify asymptotes, holes in the graph, things like that. If you're not familiar with that, not a big deal. We'll talk about that in Module 3.2. But for right now, what I'll go ahead and tell you is that there's a difference in how the function is undefined at these 2 points. So at f of 5, what we should actually see here is an open circle. So a break in the graph where that function is undefined at that point. So f of 5 should be represented as an open circle on our graph, but we don't see that in this picture. And the reason is that technology doesn't always reveal these open circles. So technology can hide certain information from us. In this case, this is the correct graph, but the way this particular program draws that, it doesn't include that open circle. They're leaving it up to whoever's doing work with this graph to understand that there is a break in the graph there. At f of 12, the reason that our function is undefined is because there's going to be a vertical asymptote. Now, in this case, this information is also hidden from us, not because the program wouldn't reveal it, but because in this case, our viewing window didn't stretch far enough to show us the behavior of that graph. So if we had changed the viewing window, what we'd actually see is this function going on and getting closer and closer and closer to that vertical asymptote, just getting smaller and smaller. We just keep plummeting down without ever crossing that line. So the reason that we don't see this is that the original viewing window for our graph was misleading. And this in particular with the TI-83s, 84s that we'll be using in this course is going to be a particular problem because the viewing window you have to set every time you create a new graph. So if you had your xmin, xmax set to -5 and 5, you would never see this behavior of this asymptote. You'd have to adjust your viewing window to go beyond 12 so that you could see that behavior where this dips down. So technology doesn't reveal the open circles or breaks in our graph, at least not always. And if viewing windows are set incorrectly, we're not going to get that full picture. So if we rely on graphical methods to better understand the behavior of our function, then we can easily be misled. Calculators, computer programs can do things to give us an inaccurate picture. So to avoid this, we'll construct some notation, definitions, and theorems to solve limits algebraically.